minute or a couple minutes to be live.
Yeah, I'll watch for it. Looks like it's going.
Cool. All right.
Well,
we're 10 minutes late. I apologize. So confirm for me, Scott, you're seeing it on Facebook? Others? Looks like people are talking. People are probably bitching because we're late. I got Chris's face on there too. Don't pick your nose, Chris. Okay.
Scott, you got an echo going on from something. I just don't know what. I don't know if it's going to the stream, but it's definitely coming to us twice.
Okay, hold on. Is that any better?
I need to sit back some, man. My face is way too big.
Yeah, did my echo go away by chance?
Yeah, okay.
I don't hear anything, but
Okay, just checking. Well, we're live. So sorry everybody who's tuning in. We're having technical difficulties because this is Clark and I'm remote tonight. So we're trying to do dyno tuning on this turbine engine thing, which is also taking forever. So we apologize, but we don't even have an intro, but we'll just go ahead and get started. Why don't I'm just going to first ask that people can hear us both on YouTube and on, it looks like they can. Looks like our stream's going through. But if you can't hear us, you can't really complain. So we're just going to go ahead. Welcome tonight. So it was asked of us to talk about ignition systems. And literally the first person I thought of was Chris Delgado at ProSpeed, because he's shown me data where he actually has logged current draw on individual coils because his installs are technical enough that typically they will have a PDM and an advanced enough PDM and a high enough budget that he can literally watch the current consumption, and that's a way you can keep track of the saturation on the coils, which, I think the general consensus, or most people feel that, you want to saturate the coils as much as you can without overcharging them. I've got some little bit of testing, but I don't know, Chris, maybe you can talk a minute about the equipment that you're using on these cars where you can monitor this stuff. And again, we also want to discuss the comparison between capacitive discharge ignition versus an inductive ignition, which is like the IGN-1A. So go ahead, give us a little bit of background and your experience with this.
Hey, Scott and Chris, before we get right to that, we might want to define some terms. We might want to set the playing field here for what we're talking about, define PDM, and define what we're talking about in terms of things like coil saturation stuff, so that everybody in the audience understands what we're trying to get to in terms of being able to light the fire effectively when we're running 65 PSI.
Okay. If you want, I can start with that, and feel free to jump in if I miss something.
Go for it.
I'll start with the coil stuff because I think that's more what the focus is. There's a few different types of ignition systems, I would say. I wouldn't really say coils because a coil is just one component of the whole system. There are what most people generally refer to as smart coils, which are, some people call them self-ignited or whatever, but basically it's a ignition coil that has electronics built into it that handle the task of charging the coil and firing the coil. And I'll get more into like how that works and what exactly that means. Then you have a CDI, which is the other kind of popular type of ignition system where the coil doesn't have any kind of electronics or any smarts in it, but there's a separate box that holds the charge and basically fires the coil. And like I said, we'll get more into that. There's another type of ignition, kind of old school, like what your lawnmower might have, which is basically a Magneto style ignition, where you're basically just generating the voltage and directly applying it to the coil all in one swoop at one time. There's really no intermediate electronics in a true Magneto type system. Now there's combinations of that. Like for instance, MSD mag setup it's got a Magneto, but it also has sort of a CDI controller, if you want to call it that. It's kind of a mix mash of those two types of technologies. Basically on a smart coil, so basically the way, let's just start from the beginning. The way a coil works, you got a whole bunch of wire wrapped around, like a spool of wire wrapped around like some sort of a core. Typically it's iron. There may be some other like fancy metals that they use. And you apply voltage to that coil, and the coil actually builds a charge internally. It builds like a magnetic flux inside. And when you cut the power from that coil, it will discharge all of that energy into wherever you've got it directed, whether it be a spark plug, your finger, whatever you have stuck in the other side of the coil. And this is any coil. This is also, a fan motor will discharge when it's turned off, a solenoid for a trans brake. And this is why and this is just kind of a little tidbit, a lot of these, when you hook up like a trans brake or like a fuel pump, or let's say a fan, like a heavy fan, they're always like, oh, well, you got to be careful with the flyback. You have flyback. Well, flyback is basically just a discharge of the coil that goes backwards through the circuit. So when you're talking about a coil wrapped around a steel core or any kind of, armature, like they all discharge when you turn them off. That's just the nature of it. So an ignition coil works in much the same way, except that discharge is desirable. That's the end goal, is to discharge that electricity that's been built up and stored into the spark plug, so it jump a gap, light the ignition, whatever. Trying to think which direction to go with it. You want to start with smart coils? You want to start with CDI? Like, where do you want to which direction?
I would probably start with the history of capacitive discharge ignition. MSD stood for multi-spark or multiple spark discharge. Back in the day, CDI was the original high performance ignition. I maybe talk a little bit about the history there, or how that came about.
I'm not super detailed on the actual history, but I can kind of explain the technology a little bit. So,
I tell you what, I can talk a little bit about it.
Okay.
Basically, capacitive discharge, the idea behind it was, okay, we'll have a pool of energy stored up, and it would discharge it, in a capacitance method, where basically you have a pool of energy started, and as soon as the field is collapsed, then that stored up energy in a capacitor is used to fire the plug. And one of the neat things about that was you could build up more energy than the original points type ignitions and coils could do. So you could get a higher energy spark, and that was handy for old school engines, especially old flatheads and stuff that had horrible mixtures, and it was really hard to light the spark, even with low horsepower. So you came out with MSD. The downside to that capacitive spark was it was a much shorter spark than an inductive type of discharge. Literally the reason the name is MSD, multi-spark discharge, is they patented or came up with a method to light multiple sparks at low RPMs that would keep the engine firing clean at low RPMs, right? And above, say, 3,000 or 3,200 RPM, the multi-spark goes away, and then you just get one single fast spark. And to evidence to this day that the benefit of that short spark duration, on high RPM applications, you don't need a lot of charge time on the coils. You can run motorcycles or two-stroke outboards. In spark systems that have to discharge much more frequently at much higher frequencies or much higher RPMs, CDI still kind of reigns supreme on a lot of two-stroke outboards and on some motorcycles, I think. Maybe interrupt me, Barnhill, if that's not the case, but for a long time, capacitive discharge is where it's at.
I think CDI probably lasted longest on motorcycles over anything. There's still a lot of bike companies, even into the mid to late 2000s, using CDI or some offshoot of it, some half-powered CDI type coil. Like right. a BMW still uses it on the S1000RR and all of their big high-performance bikes. So as of 2015.
Okay. The other application where CDI was important was using a single coil. Again, all these MSD systems were single coil, multiple cylinder, so you had a distributor. When you think about it, that one coil's got to spark very frequently to keep that engine happy. Whereas on a coil per cylinder engine, the modern stuff, you've got a lot of extra. You have 8 times as much time available on a V8 to charge as you would with coil per cylinder as you would with a single coil distributor concept. So inductive coils kind of came back when engines started going coil per cylinder. You saw General Motors do it on the LS family of engines. You saw it, I think they actually did it on some of the late Vortex stuff for the last year or two. But you saw it on, an interesting one was Mercury Marine, right? These are the guys who hired Marshall Electric to design them some coils, and a friend of ours at Marshall Electric told me, hey, these IGN-1As are going to be some of the hottest working things out there. And I tried my first set in 2005, and that's literally right when they came out on the Mercury Marine, with the 1050s, 1250s, and 1650 horsepower engines that they produce. But when the IGN-1As came out, they were individual coils, but very heavy duty, and they took a lot of charge time. You know, some of them will take 8 or 9 milliseconds to, I think, I'm going to let Chris talk about the charge time on IGN-1As. He's the master of that coil pack. But they take a lot of charge time, but that's fine when you have 8 cylinders and you get back the benefit of an inductive spark long duration. And in motorsports, as it turned out, and in my experience, I mean, the reason we have Chris here is because you got to look at horsepower per cubic inch, okay? I mean, a 900 cubic inch Sonny Leonard motor is super impressive at 4,000 horsepower, but that's still just a little over 4 horse per cubic inch or whatever, you know. What's really impressive are some of the import engines. You know, Chris has, I would guess, upwards of 3,000 or 2,500 to 2,800 horsepower, 180 cubic inch engines. You know, I mean, I know he's got stuff well over 10 horsepower per cubic inch. That requires the higher cylinder pressure. The entire challenge of sparking is getting that spark to arc that gap, and the more dense the air charge it's got to arc, the more difficult it becomes. And I'll wrap it up here real quick before I turn it over to Chris's expertise. But I was just going to give some practical experience. So one of the guys, if you know Lance Nist at Pantera EFI, he's an interesting cat, and I almost would have him on here, but who knows what he'd start talking about. But he's the one that kind of introduced me to the IGN-1As. Very smart guy. He had a test chamber for ignition systems, all right? You could put 8 spark plugs in this deal, and you could raise the pressure of the, basically simulate cylinder pressure for them to light. He would put argon in these pressure chambers, in this pressure chamber of his, and basically turn it up and then run something that he'd run different ignitions. He had a machine that would run a Magneto, right? It would spin a Magneto at a certain RPM while triggering a distributor-based ignition with CDI, and he had the IGN-1As on there. And one of the interesting things he could do is he could turn up the pressure until everything, including a ProMag 44, would give up. What I learned about that, and what was most interesting, is what happens when the spark, quote unquote, blows out. First off, almost never are you actually blowing spark out. I mean, that takes incredible cylinder pressure, incredible horsepower per cubic inch. Usually the problem with a misfire is not actually blowing the spark out, but when it does truly do that, what I observed was the spark was escaping inside the plug boot. Okay, it was going from the electrode at the top of the plug down along the porcelain, between the porcelain and the rubber, exiting along the porcelain and connecting to the cylinder head. It was finding ground that way. And that's what would happen. And what he showed me was, look, if you have an engine that's having these kind of challenges, which I've seen only a few of, you know, his advice and what he showed me was get a plug boot that actually touches the steel on the plug, that wraps all the way around the porcelain. Run dielectric grease around the inner edge of the rubber, just at the outer tip where it touches the porcelain and the steel. And what you want to do is try to keep the spark from escaping that boot. And I'll be damned, I could watch him add a couple hundred more PSI using a good plug boot and wire than he could with just standard boots that just went over the electrode. So I thought that was kind of interesting. And that's really the battle that you're fighting, is trying to keep that spark going where you want it to go. But back to the real challenge is, I mean, it doesn't matter whether you use a capacitive system or an inductive system. The real challenge is getting the spark to arc that gap so you get the fire lit. And for the most part, it's a yes or no thing, right? I've done some testing, and I know Brad Nagel might get on here and say, well, we tested at Engine Masters and we ran hotter performing ignitions. And interestingly enough, the inductive ignition, the ICE ignition, would make the most power on their naturally aspirated engines. So I don't know what the reasoning was. And you're talking like 0.1% of total horsepower output gain, but it was repeatable. And those guys would hunt small numbers like that. You know, a 740 horse engine picking up 4 average horsepower across maybe 10 or 15 back-to-back tests. So I don't know if there's a benefit. Now you've got guys today claiming, oh, I put this new MSD CDI box on my car, and everyone I've put it on it went faster. I'm kind of going to push back on that because Chris and guys like Shane Tecklenburg have some really high horsepower per cubic inch, including the world's fastest door car, right? And a lot of the stuff Chris has worked on. So anyway, that's my knowledge. That's where the end of my knowledge goes. I'm going to turn it over to Chris and kind of just let him kind of freestyle on, you know, the power distribution modules, what they're tracking, talk about saturation, and whether or not you think CDI has an advantage, or if you know what's going on there. But go ahead, Chris. Talk freely.
I just wanted to add something real quick before we get into Chris. If you have an ignition system and you have a comparable and they seemingly are equal, they both make good power, but one of them you pick up, you likely have fixed a problem that may be as simple as spark control. You know, we see a lot of different things with distributor versus coil on plug. You can see spark scatter where you'll set a fixed timing, and with a coil on plug, you'll see it just steady as can be, right on the money every time. And with a different system and a distributor possibly, you might see it wander just a little, degree or two either way, back and forth, but you'll see it jitter back and forth and it won't be as stable. And when you see that, that's spark scatter. It's not able to accurately control the spark as good as another system. So potentially that is where you see some of that power pickup, is because the spark is better controlled.
All right, tell me if it gets too loud. This guy is power washing right outside my door right now.
Lovely. Fire him.
All right, so I was going to go all the way back to the CDI side of things to start. You touched on a few things that are important to know. So the CDI is typically was more beneficial in a distributed type system because of the lack of time available to fire the coil, because you basically had a coil that had to fire eight times, right, and the same amount of time that a coil on plug only needed one time to fire, and that's a drastic difference in the amount of time available to charge. A CDI box charges it's constantly charging, so even when it fires, it doesn't even necessarily drain the whole bank of capacitors in there on that side. So it may drain it by 50%, and then it charges back up by the next hit, depending on the impedance of the coil and all that other stuff. With that being said, so I have some math here just to kind of, if you're firing one coil, let's just say one coil a second, or one coil per engine revolution, at 3,000 RPM, you have about 20 milliseconds that you can charge that coil. At 8,000 RPM, you have about 7.5 milliseconds. At 10,000 RPM, 6, 12.5, you're looking at about 4.8 milliseconds. Now, the charge time on a CDI is extremely fast, and also the discharge time on a CDI. You have to remember, like, you don't only need a certain amount of time to charge the coil. You also need a certain amount of time for the discharge. So a CDI will discharge a coil in about 600 microseconds, and that's like a slower one. Well, I wouldn't say slower, but that's some of the longer durations of the CDI on the market, which is
Note that he's talking microseconds, which is like a complete different
right.
scale of quickness.
It's like, yeah, it's like 0.6 milliseconds, which is, I mean, it's extremely fast. Compared to something like an IGN-1A, which at full saturation, it will actually hold that spark. It'll hold that arc for 2.4, 2.3 milliseconds. So I think one of the reasons why, this is just, I'm going to jump around a lot. I'm kind of scattered on this. One of the reasons why I think the IGN works so well, being that they're only 150 to 160 millijoule versus a CDI that's 600 or 400 or whatever, is that it has a much longer spark duration. So if it doesn't necessarily jump the gap right away, it's eventually probably going to make that gap because there's such a large window of time that it's trying to discharge. Just as an example, let's look at 3,000 RPM, 2.4 millisecond. That spark could potentially be lit for 43 engine degrees. Now, if you were to rump that up to, let's say, 10,000 RPM, now you've got a spark that's lit for 144 degrees of engine rotation. So you in turn take that and you compare it to like a CDI. Let's say the longest duration CDI that I could find, I kind of did some digging earlier. That's only 36 degrees at 10,000 RPM. And it's only at 3,000 RPM, it's only 10 degrees. So the inductive coils that have a longer actual discharge time will typically have the spark lit for a much wider degree range. So like basically you have more of a chance of getting a full complete burn. Let me see where I was going with this. Hold on, I'm looking at my stuff real quick. So anyway, so I think that's why the CDI was so much better for like a distributed type system, because it could fire so quickly and recharge so quickly that you could get high energy between firing events. Whereas an inductive coil, especially the older ones, you really didn't have enough time to fully charge one. Like if you try to put an IGN-1A on a distributor, it'll work pretty well, but you won't get nowhere near the full output of the coil because you just don't have enough time to charge it.
Right, and realize also that those coils have a rating of duty cycle. They need to be off a certain percentage of time to cool off at
Correct.
continuous duty cycle.
Correct.
So the problem with an IGN-1A on a distributor is, yeah, you can only, well, you want to run any kind of RPM, 4 or 5 or 6,000 RPM, you literally only can charge it for like 2 or 2.5 milliseconds. Much longer than that, and it will start to overheat at continuous use. So that's why an IGN-1A does not make a good coil for an individual coil, distributor ignition. You don't put it on a GM HEI distributor and have it work well.
Yeah,
Yeah,
so
so
guys running insane RPMs. We've run into that problem on a few guys.
Yeah, so like at 3,000 RPM, if you're running on distributor, you only have a total of 5 milliseconds between firing events on the 8 cylinder. So you take that 5% and you divide it out to a max of like 85% duty cycle or whatever during that time period. You're really only going to get about 3.5 milliseconds worth of, maybe a little bit more. But you get up around 7,000, 8,000 RPM. I mean, 8,000 RPM, you don't even have a full 2 milliseconds of window between those two firing events. So you can see, like in those type of situations, the rapid charge and discharge rate of a CDI ignition definitely is a benefit over an inductive coil like an IGN-1A. Now, when you're talking about coil on plug, it's a totally different story. I mean, let's do some quick math, and I can tell you, like, with a coil on plug, if you're doing 1 cylinder, let me ramp this over. Yeah, I mean, you really don't even start to get to the point where the coil is where the coil is over duty cycling until you get 9,500, 10,000 RPM. That's about where you kind of get close to where the max duty cycle of the coil is at max charge time. So not a lot of engines rev higher than that. I mean, there are some, but the average guy that's going to buy IGN-1A coils from the Holley catalog is not going to be running that kind of RPM. So you're not going to have any issues with that. But even that being said, go ahead.
I was gonna say, while we're kind of on that, I'm curious. I've seen some questions on I've seen some RPM situations. Running the math on what you really want to dwell an IGN-1A at, where is the say, assuming coil per cylinder, where is the RPM cutoff on that, roughly?
Well, I mean, they'll fire all the way down to like 1.5 milliseconds. So it really depends on how much.
Right. Yeah. I guess. Yeah. I guess. Yeah. Let's look at, say,
you can run them at 50%.
We've got some of these SR guys running 1,000 horsepowers in a 2.2 liter, running 10K plus RPMs. Usually the only time I've seen an issue is on motorcycle guys, high boosted guys, something like that, running 300 to 500 horsepower or more out of a 1 liter to 1,600 cc motorcycle engine. So when you're talking about something crazy high boost pressure, 40, I guess crazy 40 to 50 psi, something like that. You know, where you're going to need a decent dwell time. Where do you think the cutoff on that is?
40
Talking
or
about
50
horsepower
PSI.
wise, or
This is shit, mostly idles at that. Sorry, carry on.
no?
Well, yeah, I mean,
I mean, you can easily. I mean, we run. There's no rule that says you can't run them higher than 85% duty cycle. It's just if you do that for any duration, you're gonna burn them up. So like
Right.
white rice, I mean, we've spun. I run white rice at max saturation. It doesn't matter what boost level. As soon as it goes 1 pound of boost, I ramp the dwell up to max saturation. And we've spun the thing 12,100 one time on accident. Came back, coils were fine. But if I was to do that for 45 seconds straight, it'd probably melt all the goo out of it.
right. If we're talking, let's take a, not that these guys do it anymore because it burns shit out. Let's take a, you know, SR VVL head running, you know, 9 to 10,000 RPMs, you know, trying to make 700-800 horsepower or more.
Yeah, you could run full saturation, not
Okay.
an issue. Yeah, they'll be fine. Yep. At 10,000 RPM, you're 6 milliseconds. That's
I guess
good
maybe
amount of time.
explaining that for people might be good. You know, what we're talking about. You know, basically how long you're allowed to charge the coil for and why RPM matters and all of that.
Another thing to touch on would be the voltage that you're charging them at.
Yeah, I was just about to say that.
Yeah.
Yeah, so if you're an SR guy, you might only have 11 volts. That might be a problem. The old 240 or something. You know, if you're 16 volts, then it's not really an issue. So the voltage is very plays a big role on how long it takes to charge the coil. Obviously, the lower the voltage, the longer you have to charge the coil. So something like and actually, this would be a good time for me to put my little chart up that I have. How do you put like a graphic up?
Bottom of the center screen, share screen. Green arrow at the bottom, probably.
Okay, cool.
So just to add to that whole dwell time thing, I tell people don't think of it as your car has a voltage. Think of it as you're producing wattage, because then you can directly apply Ohm's law to it, and you can do simple math to come up with, oh, they rate this coil at 13.8 or 14 volts to be, so let's say 4 milliseconds. But if you ramp that up to 16 volts, then that charge time, instead of needing 4, now becomes like 3.5 or 3.8. I can't remember. I don't know the number right off the top of my head. I didn't actually do the math, but
you'll see this.
The higher voltage you go, yeah, it's real small. The higher, there you go. The higher voltage you go, the less dwell time it takes to get to the same wattage. And that's what you're really looking for. It's total output, total input wattage based on current and amperage and voltage all combined.
Let me add something real quick, just so we don't, I'm not saying we're going to put guys to sleep, but after the technical discussion, I think we're going to go ahead and have a practical discussion, because I know a couple people are asking, and Bill is probably thinking, well, what does this mean to me in real life? I mean, one of the things I was just going to add was, you don't got to saturate it for your application. You may be better off just running enough dwell to keep the spark happy, and then maybe 10 or 15% more current over that. But and someone was asking about plug gap. We will get to those questions. I just want to let these guys continue, because the tech and the time behind this is really important. So keep going, guys.
So here's a chart that this was independently tested, some company NZEFI or whatever, and I go by this. It seems to be pretty close to everything else I've seen, and I've actually done a little bit of testing on my own. And I've seen like other guys like Shane Tecklenburg do testing and stuff like that, and he uses similar numbers. So it's got to be in the ballpark. So basically, if you look in this white area here, this is the nominal, like where it says 8 amp. This is like the nominal dwell that you can run these coils at if you're going to run them, you know, at 85% duty cycle for 5 hours straight. And these coils will live. They shouldn't have any issues with heat. You're not going to have any problems. So you're looking at 14 volts, you're about 4.8 milliseconds, 12 volts, 5.9. You can see that's actually pretty high. Like most people would never, I get calibrations all the time with people that have these, and they got them at like 3. And, you know, their system's like 12.5 volts, you know, at high RPM. So even running them at, I would call this probably 50, 60%, the numbers are pretty high to get to that point. So, and yeah, like Scott was saying, you know, not everyone needs to run them at full power. I just do it because most of the cars that I run, you know, we run a lot of boosts, we run them rich, we need it. So rather than have to dick with it later, I ramp it up with boost, and that way I don't ever have to worry about it. But if you look over here in the far right column, this is the dwell time to get full saturation, which is approximately 20 amps, which I know this chart is really close because I've got an actual scope traced here of the coil charging, and you can see this is at 13.5 volts. So you can see it took a little over 8 milliseconds before the current actually started to kind of taper right here, and it was just over 20 amps, so about 22 amps or so. Now the current's going to change a little bit with voltage, etc. So this is just kind of one point in the whole deal, but it kind of backs up this other chart, showing that this is probably pretty dang close. So 13 volts, 7.3, 16 volts, 5.9, etc. And when you come out of boost, just run it back down here in the white area. Like put some of these numbers in here to let them cool down, between runs, or let them cool down between getting in and out of the boost. And I mean, I've had street cars that I run at full kill under saturation, but only under boost, and they've been going 2-3 years, and I've never had a coil melt. So I think if you just make sure that when you're out of high load, you back the dwell down, you can get away with running them full power, pretty much in any application. Now boat might be a different story because you're running them full time, for 20 minutes at a time.
Right.
So I guess
understanding your load is huge there. So that's where I have to educate drift guys all the time. It's like, you are full load for 45 seconds to a minute. That's way different.
Yeah.
In that situation, a road race guy.
Yeah, in that situation, you definitely want to probably back it down. But 40, 50 pounds of boost, honestly, on something like a SR VVL, like you probably don't even need to run it past 8 or 10 amps. Honestly, I don't think you would need that at that power level. 1,000, 1,200 horsepower. Like, I just don't think you would need that much. You wouldn't need to run them at full saturation. So you could probably run here in this nominal region and be happy for as long as you wanted to stay on the throttle and not have to worry about it. So, Scott was mentioning that, I have run these on pretty much most of my higher end projects have Motec PDMs. There's a lot of different PDMs out there. I just prefer, I prefer the Motec. Yeah, I prefer the Motec ones just because I've never, ever had a failure. I've never had any kind of problems with them. There are other ones out there that are less expensive, like the ECU Master one's actually pretty decent. It's equally as programmable. The downside, like with ECU Master, I've had is, like Scott has complained about on Facebook, when you go to hit the starter button, if the voltage drops just a little bit too low, it shuts the whole PDM off. The Motec
blue collar tuners have to use the cheaper PDMs, man. So I warn people, don't run your starter.
There's some workarounds on that, but yeah.
I know. I know.
Yeah, the Ames PDM finally hit the States too.
Yeah, the Motec one doesn't have that problem. I've had them stay lit at as low as 6 volts during cranking and not lost PDM control.
Yeah. It's always good to know where your electronics give up at what low voltage.
Yeah.
How low can they go? Because they'll see low voltage during cranking. How low can they still function? That was one of the things I liked about the 16-bit Megasquirt, was I could keep that thing alive at 7 volts for cranking because we had dual car.
And just to touch on the PDM thing, there definitely is a difference in quality. The noise isolation between channels, that's a big deal. I mean, when you're talking about something like the Motec stuff, I mean, those guys' only goal in life is to design the baddest shit they can design, and whatever it costs is what it costs, and that's why they're so expensive. And that's why you pay a lot of money for that stuff.
I've never once been at the track, seen or heard of Tecklenburg asking around if someone had a spare PDM. Not once.
Or even an ECU. Like, you just don't carry spares of that shit. Yeah.
Nothing like that. But I mean, I go to any popular drag race sanctioned event, an MCA race, a Ducks race, whatever, and just listen around in the pits. And when the requests go out for electronics, shit, I think I killed my smart wire. Anybody got a spare so I can check? Oh, my Holley ECU crap, my Fuel Tech crap. Well, and I think that's part of that's just the lesser cost. That's probably the difference in prices on some of these. But go on, carry on.
Yeah, no, I agree 100%. You definitely get what you pay. I mean, let's be real. You can make anything fast on just about anything. If you've got a good chassis, a good engine program, and a tuner that knows what he's doing, you can make anything pretty much fast with basic electronics, but there is a difference in the quality and the reliability, and
For sure.
it's just better tools in your toolbox. You've got your Harbor Freight all the way up to your Ingersoll Rand or whatever you would consider like the top end, and it's a preference thing. So anyway, so I've done a lot of projects with the Motec PDMs, and we do log the the coil current and voltages and stuff. And one thing you have to remember is, like, people are like, oh, it draws 20 amps, so I'm gonna need, I've got 8 coils, I'm gonna need fucking over 100 amps. So it doesn't work like that, because you're not simultaneously charging all the coils at the same time. So now, depending on the setup, if you have an odd fire engine or whatever, there may be more or less overlap between firing events. But typically on a standard V8, I've seen, like, at 7,500 RPM, 8,000 RPM, with full saturation, I'll see an average current draw across 4 coils of about 25 to 30 amps at 16 volts. So typically I'll run 40 amp fuses on a bank of 4. And that seems to be fine. I've never had an issue blowing fuses.
Same here.
Wiring is super critical. Your trigger wire and your EST ground, your coil, your logic ground can be small, doesn't matter. But your power coming in needs to be pretty hefty. I mean, you need to be able to support 25 amps realistically. And you got to remember, if it's a long wire, it's going from the front of the car all the way to, say your ECU's in a trunk. Or your batteries in a trunk where you're getting power from, like, you got to take into account the length, not just the gauge. You can't just say, well, okay, this 1 foot piece of wire will hold 20 amps, but and 22 gauge. But if you're going 10 feet, you might need to go up to a 18 or 16 gauge wire or whatever, or maybe even bigger. So
that's part of the whole deal. Like the Holley harnesses, when they sell you a harness for LS1 coils, it's a certain gauge, and if you buy the IGN 1A coils rebranded, they recommend you purchase their upgrade harness, which has a little thicker wire in for the power and grounds on it.
Just please don't power it directly to your battery or switch, please.
Yeah.
Please switch to the power.
Right.
Make sure it turns off when the ECU turns off. That's the most important part.
Yeah, no, there's experts out there telling people just wire your coils hot direct to the battery all the time. And I know for a fact, I mean, probably half the major ECUs, when you do a firmware update or even when you power up, they will cycle all their outputs, including the spark outputs.
Yep, I almost got my arm caught off by someone doing that once. While I was checking something, they updated a firmware and it started firing all the coils.
Little fumes.
Brian, everybody did that. So, but yeah,
I
always run my coil power, my injector power, all the primary powers off of relays that are switched by the ECU. So when the ECU,
I had that. Those
Go
guys
ahead.
wondering why every time I turn my key on, my coils fire and I get this backfire. What's going on? It's because your ECU is firing the coils because they're powered up when you power up the ECU.
I've seen that take a relatively expensive drag racing blower and send it up through the hood. That problem.
Oh,
So,
I can imagine.
Well, I think a lot of people they don't really have a technical understanding, don't realize that when the power is turned off on the ECU, 90% of the ECUs, the outputs go to ground. So anything that's ground triggered, which an ignition coil is typically fired on a falling edge. Now there are some that are rising edge, like some MSD stuff, but typically a smart coil is fired on the falling edge. So if it's been on for a minute and then you turn the ECU power off and they all go to ground, it's going to fire all those coils as soon as you turn the key off. So you definitely want to make sure that your coil power does turn off at the same time that the actual whatever's firing the coils turns off.
I have a question.
It's important to note. It's important to note that whole falling edge thing. ECUs often some will let you choose rising or falling edge. On a smart coil, if you choose a rising edge on accident, it'll melt that coil. Like the first time that it fires a spark, it'll melt that coil within about another 3 or 4 seconds. And I mean, just completely gone, done.
It does
no
that
chance
because
of recovery.
the resting state of the coil is backwards and it's actually the charging state.
Yep.
And so you
It's
power
full
on
charge,
and actually put the key on. That setting is one I always tell people, well, there's one right setting. I mean, then I tell them the right way, but one right setting and one that you'll figure out is the wrong setting real quick.
Yeah.
Yep. I don't have a problem admitting that I accidentally did that on one of my coils previously. It's a lesson you learn. You forget to change the setting. It was defaulted as as rising in the software, and I totally forgot and didn't look at it and melted a coil.
So guys, is this a good time to remind people about the Power and Grounds webinar that's available through RealTuners? If you're listening to this and thinking, what the flop are they talking about? This is the time to think about how you do these. IGN-1As have 5 wires going to them. You need to wire all 5 of them properly at the right gauges. Something to remember.
On Bill's car. He's like, what the fuck do I get? It's anti-terminations.
Yeah, it's all part
The
of
3
the fun.
grounds do not just go to the head.
What?
Right? They are very specific grounds.
Kidding.
Yeah.
Hey, here's a question that I know is occurring in a lot of people's minds right now. We've focused a lot on IGN-1As here.
How do you unshare? Sorry, I'm interrupting. Oh, there.
No worries.
Okay.
Bottom.
Oh, now we see you big. A quick survey of the internet shows that they run from $71 to $75 unless you're getting ripped off per coil. Now, a lot of people are sitting out there thinking, I'm going to run stock LS1 coils, or I'm going to run stock Ford modular coils, or I'm going to run blah, blah, blah. How much of this applies to those, and how much of this should we be thinking about for all of these other applications where people want to use? I want to use junkyard coils. I want to use coils I get from Rock Auto. What's the thinking there?
I'll give an answer real quick, just a low brow blue collar guy answer, and then we'll let Chris talk some more. So it's funny, old Papa John Huber, rest in peace. But John Huber, the turbo 4-cylinder Mustang guys, the senior guy there, was just awesome, smart guy, and his simple approach was, okay, grab whatever ignition system weighs the most, right? Because he knew that the current capacity, or the ultimate capacity, really is based on how much copper is wound up in total for the whole system, for the whole engine, right? And that's why a set of IGN-1As, or even a set of LS packs, weigh all 8 of those against a regular coil like an MSD Blaster 6, and they're like 5 times the weight. It's because the big part of it is being able to deliver all that energy requires, that more materials, like Chris went over 10 minutes ago.
There needs to be more storage space to store that energy so you can fire.
Right now, you can go out and Google that question, and you'll find out that GM LS packs are really, really good for OEM stuff. That the Ford coil on plugs are not that great. They can do, like everything else, Ford, they get about 3/4 of the way as good. And oh, no laughter. Yeah. Sorry. Yeah.
Yeah.
All right, that was a dumb joke. Okay, so the basic version of that is you can go out and find out what coils are good for a given application. There's some really hot, like the old Mitsubishi, the DSM coil packs. We used to put pairs of that set up on a V8, run at wasted spark. Those would do really good on a sub 1,000 horsepower V8 and last forever. But anyway, I don't know, Chris, your thoughts on that?
Yeah, just for a quick reference, I've seen a few independent tests, and most of the LS coils, pretty much from anybody and everybody that are genuine LS coils and not China brand coils, are around 30 millijoules, megajoules. What is
millijoules,
it? And the IGN-1As are somewhere around 100, 105-ish. So that's just a reference of how much more power there is in an IGN-1A, which is a bigger capacitor inside. It's a bigger coil to charge. It's more stuff to make it burn hotter.
You have to remember that 100 millijoule rating is at nominal saturation. It's not at full saturation. It's anywhere between 150 to 160 in that range. So that's drastically, it's more than double so to answer the question, there's a lot of decent coils out there, like the R35 GTR coils are decent. The 1ZZ Toyota coils are decent. Honda K-Series coils are decent. The coil packs from the old, like the SRT 4 Neons were pretty good for if you don't want to do wasted spark. There's a lot of decent coil packs out there, but there's really no other OEM coil pack that I personally come across that has even, half the output of an IGN-1A at full saturation. That's
what is it, the R35 coil that's supposed to be like the king OEM coil now or something?
Yeah.
And that's nowhere near the IGN-1A.
I think it's like
Chris only works on the wine and cheese between rounds cars. Sorry.
but the same guidelines really apply to any smart coil. You have a certain amount of time that particular coil needs to be charged. and there's a certain amount of time that it needs to cool down. And honestly, it's kind of hard to find some of that information. Usually what I do is I'll find out what factory vehicle that coil came from, and I'll pull a HP tuners file or a NIS tune file or whatever, access port file, whatever I can get, and look at what the factory values were for those. And I would imagine most of the factory values are a little on conservative side. So you can play with it. The other option is if you know someone that's got an oscilloscope and knows how to use it, you can put one on a bench and charge it and measure it. And I've actually got a folder with like 70 scope traces from a bunch of popular coils, and the dwell time and where they peak and they saturate.
Worth noting is some coils, when they saturate, will auto discharge.
Yeah,
and a lot of LS guys have found that out the hard way.
Especially those the super popular but not so great, the D535s or whatever that was the ones they're called, the LQ.
Yeah, I forget the number on them, but yeah.
And the tricky part of that is everyone's like, oh yeah, 4 milliseconds, they're fine. But you have to remember, as the temperature goes up and all the electronic characteristics of the coil internally change, that number drastically drops. I've seen some auto fire at 3.6 milliseconds that have been like really hot, like when you mount them inside a 2JZ head, for instance. So they don't get any kind of cooling. So you just got to be careful, like do some research. If you're going to use a coil that is not super common, like look around, make sure that it doesn't have any issues with auto firing.
Yeah, we actually found that out the hard way over the weekend on the Miata coils.
Yeah.
Apparently, and it actually wasn't my problem. I did melt a coil on my car on the track this weekend. And apparently,
but it definitely wasn't
Miata
the tune, because you're hearing from the tuner.
Yeah. In my case, it was a mechanical failure and it was cracked, but it started this discussion, and it apparently those coils will start to, on a road race endurance application, when they get hot over 1.5 milliseconds, and guys are seeing the coils melt. And I was running too.
Yeah, I've seen coils that as low as 1 millisecond. Like some of them just don't need any charge time at all. It varies drastically. And I don't necessarily think the charge time is directly related to the power output. I think it just more has to do with the electronics inside, the impedance of the actual coil itself, versus the electronics that are charging it. So just because one coil has 5 milliseconds, dwell time, and one coil has 3.5, doesn't necessarily mean the 5 millisecond charge coil is going to put more output. It just means that electronically it just takes that much longer to fully charge the coil.
This may be a hick statement, but my theory is IGN-1As have heat sinks on them. And if something has a heat sink on it, that's intended to dissipate heat. So therefore, it's worth spending a minute or two thinking about where the coils are located so that they actually have an opportunity to get some airflow to dissipate that heat. Might not matter in something like a 1,000 horse NA application, but it might matter a ton in a 3,000 horse, turbo application where the underhood temperatures are 1,000,000 degrees.
Or even a quarter mile versus a standing mile.
Streetcar applications can find a lot of heat under the hood, especially sitting in a parking lot for an hour or 45 minutes after it's been run hard on a hot day in Phoenix. I've been having this. You got to be careful where you mount those, because those heat soaks can actually suck heat into the coils from outside. So that airflow is a big deal on those. Go ahead.
That was a big issue we ran into on the 2J with the LQ9 coils. Like they're actually pretty decent coils if you don't overdwell them. But the problem is, in order to fit them in the head area, you would take the metal coupled holder off of it, which A, cut back on the ignition noise, and B, acted as a heat sink. And then you're sticking them in between, two big cam tower like sections of the head, and there's just no cool air getting in there.
Were you guys running the bracket over them to hold them down too?
Yeah, by the time you're said and done, they're probably, their operating temperature is probably 3 or 4 times what it was in an LS truck, where they're out on the edge of the valve cover. There's airflow around it, So you definitely got to keep heat in mind when you're setting this stuff up. So
I just popped up a little Excel sheet just because a couple people are asking about dwell voltage stuff, and I thought this would be prudent to the whole conversation. For example, we're talking about, some of the chats were mentioning that certain coils auto fire above a certain time, right? Or they fully saturate after a certain time. And you can figure out that saturation. If you can find one voltage value from the manufacturer, from any one thing, if they say 12 volts, they saturate at X amount. If they say it saturates at 4 milliseconds of dwell, then you can look at your existing voltage of whatever you're doing and see what it's doing. So example, I'll say a 13.8 volt alternator, a current, if they say it saturates 12 volts at 4 milliseconds, you can see that at all these different voltages, exactly what it takes to saturate the same amount of current and power, right? The higher voltage you go, the less time it takes. So a 16 volt car, right, that same 4 milliseconds of dwell needs to be reduced to 3 to keep the same saturation. If you still have 4 milliseconds at 16 volts, you potentially oversaturate that coil that's only rated to be 12 volts. You can still run it on 16, but it wants less time to get to that full saturation.
Just remember that the charge rate is not necessarily perfectly linear. So this would be like a good ballpark, but you know, if the thing's getting hot, you might just have to back it down a little, you know. So always kind of at the end of the day, like use your instincts, and you know, if you run it on a dyno and you reach over there and the coil's like smoking hot, you know, you might need to back it off a little more or whatever. You know, it's definitely a good.
Yeah, Fred G had mentioned. Fred G in the YouTube chat had said his coil's auto-fired when soaked at 4 milliseconds. Realistically, that coil was probably a 4.5 millisecond time that it's going to auto-fire, but at 13.8 volts, it's close to 4 milliseconds.
What about, I don't know how he's measuring that. If he's just looking at what the ECU reports, some of the less costly ECUs may not be reporting accurately. Right. They may be applying a voltage multiplier to the dwell themselves in the background. Some of them do. It's good to know how your ECU works. But so it may not have been a real 4 milliseconds. It may just have been commanded or calculated. That's where an oscilloscope on the trigger outputs is nice, because you can see your actual, what the ECU is actually doing versus what it tells you. I bet you that he was getting more like 5.5 or 6 real dwell, because that's what I've seen set those coils off just like Chris. My answer has always been use them in lower power applications and don't come anywhere near that limit at any point in time. Run them at a maximum of like 3.8 or 4 milliseconds.
I mean, my recommendation is just use,
and especially if you're just street driving.
I know Chris is right. Use a better.
Just use IGN-1A. I mean, you're not really saving a lot of money by buying any.
You can get it for free. Pretty much.
Yeah, I mean, unless you're getting them for free. I mean, but I mean, a brand new LS coil out of the box from GM is not cheap either. Like you're not really.
And then your part store coils a lot of times are going to be worse off than your junkyard OEM coils.
Yep.
Yeah.
I mean, at that point, you got to spend
Scott, you mentioned
for an IGN-1A if you're in the coil pack world.
Yeah. So you mentioned cheap ECUs. One thing to note too in your ECU, I've seen a few ECUs do this, is make sure that their voltage reference that they're using for your dwell table is accurate and matching what you're getting at your coils. Because some pull their voltage from a different spot.
Also, make sure that whenever you're wiring these, always run your logic ground back to the ECU somewhere, because if you ground it to the head, like for instance, let's just go back to IGN. It's got specific grounds for your logic ground. And what the logic ground is, for people who don't understand, the logic ground, you have to think of a self-ignited coil. It has an electric switch inside. I'm going to try to make it as simple as possible. It's got an electric switch inside that tells the coil when to fire.
It's a relay, but it's fast. It's just like a PWM style relay. It's got a transistor.
Yeah. So, and basically what this does is the coil, it tells the coil how long to charge. Well, it doesn't tell it. The ECU tells the coil how long to charge and discharge, but the ECU, I lost my train of thought. Basically, you need the switch to be on the same plane as the ECU, because if you, let's just say you ground that to the head and there's a 0.5 volt offset between the logic ground and the ECU. The ECU thinks it's at 13.5 volts, and the ground in there is -1 or whatever from the ECU. Then your dwell is not going to be correct when it's charging. It's not going to.
Hold on a second. I got a simpler way of explaining that was
trying to think of how to explain it.
No, well, there's the transistor very much needs to know what was considered 0 volts, because there's always current riding around in your electrical system, whether you think it is or not. And you know, in grounds especially, and the problem is that the transistor inside the coil, the switch he's talking about, needs to know what 0 is, so when it sees the trigger voltage or current come in, it knows that it's off the actual 0. If you've slid that 0 around 1.5 volts or 2 volts, which can happen if it's hooked to the head, because the head is seeing, you know, spark energy ground return as it is, the cylinder head's already handling a whole bunch of noisy current. back to negative. So if you use the cylinder head grounds for the ones they tell you to run back to the ECU, you'll get weird firing behavior. But so it's really important that the switch is hooked to the ECU on their own ground plane, and that's the same reason your TPS sensor, your map sensor, your coolant temp sensors all share that one ground circuit that doesn't go to the chassis or cylinder head, it goes to the ECU.
Right.
Don't you also see? You could also see false triggers if it actually potentially
All the
activates
time.
that transistor
All the
when it
time.
does. It's not supposed to, and that's bad juju.
Mhm. And the other thing too, like your power ground and your head ground. So the ground that goes to the head is basically the other side of the coil circuit. It's designed to give you a direct path for the spark to travel. So it's important that those grounds go to the head, because if not, if they're going to the battery, then basically theoretically the spark is traveling through the spark plug, through the head, through the chassis mount, through the car, all the way back to wherever your battery ground is. So by having that head ground directly to the head, you're reducing you're reducing the potential between the spark plug electrode and the base of the spark plug where it needs to fire to. So it's very important on the coils that have their own ground for the head, that you put it on the head, on that bank. Like if you got bank to bank, like you want it as close to the spark plug as you can get it. That's going to give you the best possible transfer of electricity through the spark plug that you can get.
And the IGN-1A has a power ground, a head ground, and a logic ground.
Correct. And the battery ground,
the power ground can go to the battery. Yeah,
the reason why they like to put that on the battery is because the majority of the noise will be dampened through the battery.
Yep, so that goes along with, if you've ever watched the Power and Grounds webinar or sat through one of my classes, the sleepier parts, when we talk about noise coupling, it's important where you route both your power and your ground returns for all the different devices in the car, including the ignition system. Think of it as the device, because you don't want to have the ECU having to draw power or share a ground with a path back to the battery that's got a ton of noise on it. And again, this is where an oscilloscope is just a super handy tool to observe the different noise on the different paths back to the battery. This is also why they have the star grounding and power method, where if you could, every device would have its own power and grounds all the way back to the source. And you'll notice, for the same reason, ignition and ECU systems usually come with dedicated battery power and ground wires or harnesses for that same reason. But sorry, I didn't mean to go off on a tangent there, but you're covering the noise coupling thing that I've observed.
Yeah, I was figuring you were going to jump in on that one.
I mean, I made my living for a couple of years just going around and fixing this on different cars. It's kind of funny.
Yep. So one of the other, so I guess we could touch on, unless anyone has any questions. I'm not looking at the feed if someone wants to look at the questions, but one of the other things that I feel like
I got a good question.
Okay.
Looks like a couple people have asking about coil wire length, right? Because we're talking about the coil itself, but we haven't been talking about the other parts of that ignition system that make it actually happen. You can have a great coil and doesn't do squat unless there's a wire and a plug connected to it as well. And people are asking about wire length, and my experience and Scott Clark's experience and most of our experiences, it's not necessarily where you place the coils, because a lot of times it's working on the car factory. It's a matter of being able to physically do maintenance on the car at the track in the middle of the heat when you've got 30 minutes or possibly less to do a turnaround for the next round, depending on how the race is going. And where that coil lands is really just kind of up to where you have space and where it makes the most sense for you to do all that. Is it better to put it closer? Does it really matter? That's kind of the question people are asking, because obviously tons of people put them down in the wheel wells, they put them up in the firewall, they put them LS right on top of the valve covers, So what have you seen in practice?
I was actually about to kind of lean towards this direction. So one of the other things that has been I've actually seen more than one time when it comes to noise and stuff like that is so the shorter wire is obviously better, right? You want to have the shortest distance from the coil of the thing. You can't always accomplish that. It's not always feasible, and that's fine. But you also have to look at the quality of the wire and the resistance of the wire. If you're going to run a really long wire, you want to be careful not to run one of these like zero resistance, low resistance wires, because the lower the resistance in the wire, the more noise that that wire is going to put into other things around it. That's one of the reason, you know, and just an example, I was dyno jockeying a car for Shane Tecklenburg one time. It was the M2K mile car. They were using my dyno, and Shane was remote, and I was in there with the laptop, and we spent about a half a day trying to get this thing to make clean pools. And every time we do a run, the boost control was shut off. The EGTs would drop out. Like, we were having all these weird issues with the car, and we couldn't figure out why it wouldn't do clean runs. You know, we were checking everything. Like, we got to the point where I pulled like the ECU out of the car and I stuck it in the freezer for like 45 minutes, and I threw it in the car real quick to see if it would run normal. And then we'd run the car and I'd heat it up with a heat gun, like super hot, to see if it would start acting up. Like, we couldn't pinpoint where the problem was. So we were just thinking, well, maybe it's heat related, maybe it's vibration related, maybe there's something loose somewhere that we're not finding. So it turns out, after all this shenanigans and rigmarole and all this stuff that we went through, at the end of the day, you know, Shane actually messaged me, or he messaged the owner, Kevin, and I was right there. He's like, do something. He's like, order a set of plug wires from Magneto, have them drop ship to the mile, and swap them out when you get there. I was like, okay, well, that's kind of weird. I would never think that would have anything to do with it. So we got to the mile, and we swapped out the plug wires, which I think were some, I don't remember what kind they were actually, to be honest with you, the original wires, but we swapped them out with some other wires, that the Magneto, which are like 1,000 ohm a foot or something. They're really high resistance wires. Threw the wires in the car. The first pull, every single thing on the car worked. Boost control worked. EGTs were reading, no breakup. It went right down the track with no problems. So I was like, well, that's kind of interesting. So I started doing more research on the wires, and really the kind of common perspective is that the higher resistance wires have a lot more noise rejection, sort of like a resistor spark plug. You know, if you run a non-resistor spark plug, you tend to have a lot more radio frequency emitted from around that area, and it will mess up certain electronics, especially on factory cars. There's a lot of factory cars, if you run a non-resistor plug, will cause issues with the factory electronics. So the plug wire is just as critical, because after the plug, what's next? You have the wire. So you're trying to dampen noise at the, or, you know, you're trying to dampen noise at the plug, but you've got this wire that's in the same situation as a non-resistor plug that has no resistance, no noise damping, and it's causing other problems with your electronics. So this is another thing to keep in consideration, especially if you're having noise issues. I don't know if you had that guy from Firecore on. I remember, I think he touched on that a little bit, how their wires are very good with noise rejection. And some of, I guess, his top field teams, I think he was saying the EGTs would drop out or something, and they swap wires and it solved the issue. I think, if I remember, that's how the story went, sort of. But just another example of the same kind of phenomenon. So you know, if you're having weird issues with electronics and misfiring and stuff like that, like, you know, it could just be that the plug wire that you're using is not really up to the task, or because of the way you have things positioned in the car, you may need a higher resistance wire that has better noise rejection in order to have success.
The way you can use an oscilloscope to see that is just get on your common power and grounds, or power and ground source of whichever system is having the problem, and take a look and see if you get a rhythmic noise pulse, a visual spike in current or voltage. You can see it on a simple scope, like a snap-on scope works great for this, but you can see if there's noise. You can pull, you know, kill one of the coils on the engine and see if one of those pulses goes away, and you can track if that's an ignition problem or not in your power and grounds. It's a way to diagnose what they were having go wrong. I mean, I've run into that a couple times too, with plug wires.
You can see it on a $30 DIY scope on like cheap build-it-yourself sites.
Yes, exactly.
So something else that Scott touched on earlier that is super important, I think we should talk about it again, is the plug boots become more important the higher the output of the coil is. You have to remember that the spark is going to try to take the path of the least resistance. So anywhere that there is an air path between the electrode and a ground source, it's going to try to go that direction. So like if you have we'll just stick with the IGN 1A as an example. If you use the wrong kind of boots on the thing, the coil has enough power where it won't even go to the spark plug. It'll jump from the tower of the coil out from underneath the boot to the bolt that's holding it onto the head. Same thing if you have you know, a too short of a boot, or let's say you have a boot with where the actual electrode inside the boot is pulled too far back in the wire, or pushed too far forward in the wire. So when you push the boot down over the plug, the actual rubber of the boot doesn't seal airtight around the porcelain. You know, you start getting a little bit of cylinder pressure, and it's easier for that spark to jump from that electrode underneath that boot to the base of the plug than it is for it to jump the gap in the chamber, and it's going to do that. So it's very important when you're dealing with high cylinder pressure pre-combustion, just, you know, that word's used in two different ways. When you're dealing with high pre-combustion cylinder pressures and very high output ignition systems, you need to make sure that the boots are built correctly. The boot should be pushed all the way down over to the base of the plug. It should make an airtight seal around the base of the plug. Same thing on the coils. When you push the connector on the coil, it should push the air out of the connector when it goes into that coil, and it should be as airtight of a seal as possible. I know a lot of guys use dielectric grease. I don't use it. I've never really used it.
Thermatech themselves put out a thing on stop using dielectric grease in the way that most people use it. But
yeah, I've never really used it. I don't know, you know, if it's good or bad or whatever. I just never used it.
It told me only use it around the very base of the rubber where the boot makes its final contact. Like that was to make it help with that air seal.
So I have a picture here, and this is just something that I actually used this the other night on a remote tune customer that was having misfires. A really easy way to tell if a spark is jumping around the boot is when you look at the when you look at the spark plug, pull it out and look at the porcelain real closely. And if the spark is jumping around the boot, it will actually erode the porcelain where the spark jumps across. So if you can see in this picture, you'll see like little lightning bolts. They almost look like cracks in the plug, but they're not really cracks.
Carbon trace.
So if you have a car that's misfiring and you can't quite figure out what it is, pull your plugs out, look at the porcelain, the white part, and look for these little witness marks here. And if that's happening, it's because you don't have a good seal between the boot and the plug base, and what's happening is the spark's jumping from the tip of the plug all the way down to the base, and that's where your misfire is coming from. I would say 90% of misfire issues I've run into have been because of poorly built or improperly installed boots on actual plug wires. Now, if you have a coil on plug, like a physical actual coil on plug, you can still have the same problem when the boot part actually starts to wear out. And what I've actually seen on some coils is there'll be like a tiny little pinhole in the side of the boot part of the coil, the part that goes down on there, and you'll just see a tiny little pinhole with like a burn mark on it where the spark just wants to jump through, and it'll jump through to the head or jump through to something metallic around it instead of going to the spark plug. So another little thing that I've run into, like sometimes you can't see on the plug wire where it's jumping through. So what I'll do is when I pull the plug wires off, I'll bend them like in a horseshoe, and I'll roll them in my fingers, because when you bend them, if there's any little tiny hole or like fissure in the wire, when you bend it, it'll kind of open up and it'll be easier to see visually. But most of the time there's like a burn mark or like a tracking around the hole. But I see that all the time. It's a very common failure, and it's something that a lot of people just don't catch. So
another hillbilly method for that is run the car in the dark.
Yeah.
If you've got that kind of leakage, you'll get an interesting light show. Chris was mentioning about plugs. He was referring to the show that we did with Rich Gorski with fire core wires. And my apology for the noise here at home. Dogs are impatient. Anyway, those fire core wires really work. And one of the things that they feature is something they call a Pro Mod boot, which really seals around the plug, and it makes a very distinct feeling when you get it there, and that solves a lot of problems. My apologies for my dogs.
That's all right. Even with a good boot, you still have to make sure that the boot and the relationship between the boot and the actual electrode on the end of the wire is in the right position, because you can have a badass boot, but if that electrode's a half inch too far towards the end of the boot won't actually be able to sit all the way down on the porcelain properly on the plug. So when you stick your plug, even before you put them on the car, like just hold your plug wire, stick the plug in it, and if the boot doesn't go all the way down to the base of the plug, then it's not going to be the best situation. You're going to want to pull that electrode back up in that boot a little bit to where you get a full seal around the spark plug. And 90% of the time, that will solve most misfire problems. it's a common issue that people don't really think about. It's just one of those things. I see them all the time, even like from O'Reilly's, like factory plug wires. You stick them on there, and I'm like, man, this thing's like not even covering like half the plug. Like it's barely sealing around the middle part of the porcelain. So you just pull that wire back a little bit in there and get the boot all the way down in there, and it will make a significant difference in most cases. One of the things I did want to talk about or mention is that there's nothing wrong with CDIs. Like, I don't want people to get the wrong idea. Like, oh, the IGN1A is the baddest coil on the planet. That's all you should buy. I'm not saying that. There are very good CDIs out there. The new MSD CDIs looks pretty awesome. M&W has always made really good CDI boxes. I've personally used the FT Spark on a couple of cars now that weren't Fuel Tech cars. And it works. I mean, I haven't had any issues with it. You can run a 60 plug gap at 60 pounds of boost, and it gets the job done. My only argument is that for the average guy that doesn't want to spend $2,000, because you buy a CDI box, it's $1,700. Then you got to buy the coils, which is another $70 a coil. Like by the time you spend all the money,
it'll pay for the install.
Yeah, it's a more expensive. I'm not by any means saying that it's not a good solution. I'm just saying that it's a much more costly solution, and it's not necessary for probably 90% of the setups out there. You can get a lower cost IGN1A setup, some good wires, and you're going to have good success with it. So, I mean, all those graphs I posted the other day on Facebook is a perfect example. I mean, 3,800 horsepower in one car, 3,000 on another car. I've got 2J motors, running 85, 90 pounds of boost with no issues on methanol with them. I did run into a problem on one car. At around 90 pounds of boost, and we swapped over to an FT Spark on that car, and it definitely fixed the issue. But I don't think the coil was the limitation. I think it's the original wiring that was in the car, because the wiring that was in there is super messy, and when we were changing it out, I'm like, man, this is pretty bad. So it probably would have gone farther if we had redone the harness, but the time crunch, it just wasn't a viable option. It was easier just to swap a CDI in a car and call it a day. And Fuel Tech was actually nice enough to just send me one to try. They're like, hey, don't take our word for it. Just try it out. Put it on the car. Next time we went to the track, it went right down, 95 pounds of boost, no breakup. It was super clean. So, I mean, there's definitely a place for CDI boxes. They definitely work well. But for the average guy that's not trying to make 3,000 horsepower and, that's on a budget, the IGN1A is more than enough for those types of projects.
I'd say they're reliable up to like 10 plus horse per cubic inch with all of the proper cabling, proper boot, proper installation, no noise coupling. They're really good in a junk environment up to like 6 or 7 horse per cubic inch. If I had to give some numbers out, when people need to start thinking more seriously, it's pretty easy to do 5, 6, 7 horse per cubic inch with, regular Summit parts, I guess, for lack of a better term, cheaper wires, etc. But that's kind of the break points for me anyway. Just a rule of thumb I use personally.
Yeah.
They're good enough to go 3s in the 8th.
Yeah. Yeah.
We went 3s in the 8th with Larry Larson's truck on the Distributor, but we had a 7,000th gap on the plugs because we were having problems. I was having to do things to keep the spark, even at like 35 pounds of boost on his big block, to keep the spark happy when they had chosen a distributor ignition. Coil packs at the time were not being used. They were using mags. His choice would have been a mag or a distributor. He had to use a distributor plus an MSD setup because he was driving down the highway as well, indefinitely. So he couldn't use a radical race ignition. Well, we were having problems with the spark jumping out of the distributor. We went so far as to replace, and a lot of guys know this, we replaced the metal screws that hold there's 4 different metal screws inside your typical MSD distributor. I think it's ones that hold the cap together and the rotor as well. There's some, but anyway, you replace those with plastics because they were actually conducting spark out the distributor. They were presenting a less resistant path for the spark energy to travel out when there was a lot of cylinder pressure. So we were doing weird stuff with silicone and things like that, and got it to work by the end of the event. And he did his whole let's see what he ran on. His 595 pass was still in that ignition. So anyway, just a little bit of a story from experience that the kind of challenges we had with a distributor on that setup. But we did still make it work. You know, what was his 8th time? It was sub 4 seconds, whatever it was.
Yeah, what's interesting is the guys that are like pulling the magnetos off and putting IGN-1As and going just as fast without issues. I've heard of a few
The
people
car
doing
starts
that.
and idles and takes off and gets on the brake better because
Yeah,
the magnetos have less spark output at lower RPMs. They don't
So-
really start jamming until you reach a certain RPM. The other thing the magnetos have is an internal phasing issue where they're self-generating power. You know, they generate their own power. So the thing is, there's a certain spark timing. There's a certain time in crank degrees where those things are ready to deliver the most energy. If you try, so you got to adjust the magneto so that its peak. This is one of the things that David Wolf did with his modified magnetos was he'd make a little mark so you could phase the distributor body or the magneto body, you know, and it had a little T symbol that was like that lined up with a hole in the case, and that you knew that was where the spark discharge was maximum performance. So if your engine made most of its power on 24 degrees, you'd phase everything for 24 degrees with a magneto. On top of the fact that if you're using a points box or an external ECU to trigger the actual firing, you had to time that properly as well. Those earlier pro mods with these ignitions were really hard to get phased right.
Yeah, actually, I was going to touch on that. I spent some time with David Wolf a couple years ago, and he showed me he has this whole bench thing set up. We put the magneto on there, and he has a scope and a light and all this stuff, and he would run it and he would rotate it, and because basically the magneto is basically just a generator, and it works on a wave. Like as the magnet comes by, that magnet generates this AC voltage, and depending on where that thing is phased in relationship to where you want to fire the coil, you may be on the the upward slope, the middle, or the downward slope of that phase. And
Exactly.
that's one of those things where, like, the first time I ever did a mag on a car, the guy's like, yeah, it won't start unless you put it like 30 degrees advance. And I'm like, man, 30 degrees advance, you're probably going to break the starter off the thing. And it was because the magneto wasn't phased properly. And I went back and I was thinking about what Wolf was saying, and I thought about it, like, oh man, if we move this a little bit, then it'll probably start at 15 degrees. And sure enough, we moved it and got the because what was happening is if you try to crank it at, say, 5 or 10 degrees, which is reasonable for a big high compression engine like that, it wasn't far enough into the wave to actually generate a spark. So like there was just no fire until you got a little bit further. We were actually on the downside of on the backside of the waveform. There wasn't enough energy there to actually light the plug off. So we had to move the magneto a little bit to get that voltage generation at the right point to where it would start with less advance in it and stop breaking the starter rings off. So it's kind of interesting. Magneto is a whole other animal in itself, and it's very interesting how they've been around for so long.
Do you know how much power it takes to drive a magneto at RPM?
Not as much as people thought. I saw that test happen. It was, some people are like, oh, it takes 100 or 200 horsepower. I think I heard one guy try to say on a top fuel dragster. It wasn't. It was something like 30 or 40 horsepower on big power engines. And I saw that on Proline did a test on their engine dynos with engines that were making in the car, 3,800 to 4,000 horsepower at the time on the magnetos, and they were testing the power soak of driving a magneto, and it was like 40 horsepower on those engines, that were running up to 8,500 RPM.
That makes sense.
Yeah, so I mean, the interesting thing was magnetos used to just be fixed phasing. If you don't hook a points box, is what they call it, but it's basically an external trigger to actually fire the spark. If you don't hook one of those up, the magneto will just always fire at, say, 30 degrees or whatever you have it turned to, and it's not a problem. You line up the T with the hole in the housing, and then you drop the distributor in at the timing that you want, or the magneto, I mean. But when you started having computers trigger them to be able to advance or retard that timing off of their centered base, that was when the challenges of phasing became like a two-layer problem, and people struggled with when they started integrating magnetos with ECUs.
It's definitely super a pain in the ass if you don't understand it. Luckily, like you did, I got to spend time with David Wolf, and he explained it to me. I was like, oh, that's pretty neat. And next time I had to do it, I was like, oh, I could fix that. There you go. Now it's good.
Yeah. So I didn't actually ever get to meet him, but Mark Woodruff, such a cool guy. Like, he himself we were struggling with a Magneto on. Oh, they were doing it on Keith Barry's car. One of his engines, when he switched over to the big bore space small block or whatever, they had a Magneto for a while, and they were triggering it with an ECU. And I understood how the ECU worked and triggered it, but I did not understand the internal phasing of the Magneto. And I knew by turning a spare one in the trailer, all right, there's 4 notches in this thing as it goes around. It's actually obviously got points where it's charged better. Woody's like, oh man, we'll take one of these apart. I'll meet you Sunday morning. We show up. He's like, show up at 6 or 7 o'clock or something at the track in Florida. And he's like, I'll take you through it. Joe Oplowski, you guys know Joe Oplowski up in Chicago, another real good, popular Radio versus the World radial car tuner, M-Tron guy. Anyway, tunes Tim Slavin's car. He was there too. He showed up when Woody walked us through disassembling a Magneto and explaining how it worked and how the phasing worked. And he's like, and this is a David Wolf modified one. You know, you always want to send him off to him because he actually makes it so you can line it up and see where the highest energy point is, that you can go ahead and trigger a spark at that point, you know, base everything around that. So that was who I learned from. Woody Woodruff, Mark Woodruff is a good dude. He showed us how that worked. And that was, God, that's like 10 years ago. Jeez. Anyway, go ahead.
Yeah, any questions? I've kind of covered most of what I was kind of planning to cover.
So there was a question on the YouTube side of things. I'm trying to go back to this a little bit about you know, people running into issues, and this might not be right on point for you, but running into issues around distributor phasing and firing phasing and nitrous motors. Any comments, anybody on that?
Get rid of the distributor. Yeah, I've run into this even on a turbo car. Like the first,
Yeah, but right. Get rid of the distributor, just even for naturally aspirated stuff.
Yeah. The first big power turbo car I did, probably on a distributor, I should say, probably 7 or 8 years ago. It was an XT75 car, and for me at the time, that was like a big power car for me. And you know, with the 6-cylinder stuff, I would make as much boost as I could on the line. I would do everything with timing, and I kept raising his launch boost. You know, we got up to like 15, 18, 19, 20 pounds, and I was pulling, you know, like 10, 12, 15, 18, 20 degrees on the hit, and I was just controlling it all with timing. And we went up there, I pulled another couple of degrees out of it, and I put another couple of pounds in it on the hit, and he went up there on the line. As soon as he let go of the button, the car's like bah, 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 and just died. And I'm like, what the hell's going on? I couldn't figure out what it was. And that was my first experience with running out of phasing on a distributor. You know, it got so far off the alignment between the rotor and the post got so far off that it couldn't fire anymore.
Or it would spark to a different tower, and then you have real problems. Yeah.
And at that point, it clicked in my head. I was like, holy shit, like I never want to use a distributor ever again. Like this
yep.
sucks.
So I tell people that the two things, the greatest thing about a coil per cylinder engine is you can light the spark anytime during the combustion cycle that you want. There's no limitation of a mechanical distribution device.
And there's no chance you can accidentally move it, and it's
but also the worst thing about the coil packs is that you can light the spark at any time. If you have noise problems in your electrical system and the power supply or the grounds, or noise in the ground we talked about that goes back to the ECU, the reference ground, if you have noise problems, you can end up with spark triggering by accident at, say, 90 before top dead center on a combustion stroke, which is something you can't really do on a distributor. It kind of keeps you somewhat safe. And in which case, under big boost in the middle of a track pass, that's going to send rods flying out the side of the block.
Yeah, I was about to say that'll make the crank exit.
Speaking of that, one little oops I had about 10 years ago that might be beneficial to somebody listening one day.
He's lying. It happened last week.
Yeah, no, definitely. So when you set up a CDI box, especially like an M&W specifically, because I know they're this way, make sure that you set the edge of the actual CDI box to match the firing edge of the ECU. And the reason why this is important is because if you have the edge reversed on an M&W box, which is a really good ignition box, the timing will actually advance with RPM. And I found this out on a 1,000 horsepower Honda Civic, where we cracked all 4 chambers, and we actually bent a set of brand new aluminum rods. Surprisingly, it didn't break anything other than all the chambers were cracked where the spark plugs are. But and we I didn't even realize what happened the first pull. Like, we did a pull, and it made like 4 something, and I'm like, man, this thing's on like 45 pounds of boost. It should be making like 800 something, and it sounded weird. It was on a Mustang dyno, so the pull was already like 30 seconds long. And we let off. I pulled the plugs out, and the ground straps were gone. I'm like, okay, well, that's not good. And so we put new plugs in it, fired it up, and it ran okay, but it didn't sound quite right. And I'm like, well, that's weird. So like, my first thought is, man, the timing must be off. Like, maybe, the cam angle sensor moved or something, because we had one of those AM CAS on there. So we put a timing light on it and checked it, and it was right on the money. I'm like, well, that's weird. And I revved it up, and I saw the timing. It went from 0 to like 65 degrees, like in a matter of like 0 to like almost 5,000 RPM. And at that minute, I knew exactly what had happened. So you got to be very careful when selecting your edges, that your output, your firing edge in the computer matches the firing edge that the ignition box is set up to look for. Because if you get them backwards, you will get a extremely
something else we should add. I know Evans is probably thinking this already. Inductive delay is a setting you'll see like in your Holly and in your Megasport and in your everything. And what it is, if you still have, when you lock the timing and you rev the engine and it still moves a little bit, 4 or 5 degrees across a 5,000 RPM sweep, adjusting the inductive delay number usually will help you make that more steady. And the reason it does that is it's you're telling the ECU, hey, how much time is there between the time I command the spark to where the spark actually happens? It's letting you compensate for the mechanical delay in between, those 2 points in the system. So if you get that, what happens is that's a fixed number, but that cumulatively as RPMs go up, that becomes it throws off your time between events, because the events get closer together, but the delay is the same. So it can actually throw your timing off. So you use that inductive delay parameter to adjust that. Sorry, go ahead. You may have a better explanation.
No, that was good. There's actually 2 different sides to that too. If you're using a VR sensor, once you get to a certain point in the RPM,
you mean for your crank position, right? You're an inductive pickup sensor, a 2-wire sensor, or magnetic.
Correct.
They call it, but the 2-wire sensors.
Yeah, so those have a naturally shifting. They'll naturally shift just slightly at higher RPM, just because of the nature of the waveform and the time. So you have that delay, and then you have that movement, and then you also have the delay of the actual coil from the time that the ECU commands it to fire and the time that the spark actually happens. So there's actually more than one. And some ECUs will allow you to adjust for one or the other or both, and some of them are by RPM, some of them are a fixed number. It just depends. So make sure you're familiar with which factor you're correcting for in the ECU, and how the ECU applies that correction, because it's not always the same in every situation. Most ECUs, like basic stuff like Holly and big stuff and fast and stuff like that, it's just a basic adjustment. It's not a big deal. But some of the more advanced ECUs will have multiple ways to fix that problem. So just make sure you're familiar with that if you're going to mess with it.
Someone was asking, how does a normal guy with a basic cheap oscilloscope test the saturation point, and how long to run the dwell for? Let me give what I've done and observed first, and Chris probably has a better way. I know Chris actually has some systems on board that can monitor the current draw, but I know that if you have the add-on to an oscilloscope, like an inductive probe, that's set up for metering spark ignitions, like the old Sun systems, you can sometimes find one of these inductive pickups, the same thing that's on an inductive pickup for a timing light. You can use one of those add-ons for an oscilloscope, and you can actually monitor the voltage that it'll convert current into a voltage signal, so the oscilloscope can read. So you can monitor the spark energy. You can sit there while it's idling and keep adding dwell until you don't see that peak get any higher. That's one way to know you're saturating the coils. And the other way is, if you didn't have that add-on, you could look at the current that's being fed to each coil, and if you have something like, again, an oscilloscope can monitor how much current is being used. Once the current consumption doesn't get any greater, you know that you're saturated the coil. And I don't know, Chris, is there a better way?
That's probably the best way to do it, honestly. And if you don't have a current probe, you can drop a resistor between the 12 volt and a ground, and you can measure the voltage across the resistor, and that will give you basically it's I guess a calculated current, if you may, but you'll see it rise and taper off, and so if you don't have if you don't have a current clamp for your oscilloscope, I think I believe it's a 1K. If I remember right, it's a 1K, or it's either 1K or 100 ohm. I'd have to look it up, but you can drop it between the power and the ground reference, and then you measure voltage across that, and that voltage is going to be like millivolts is basically milliamps is how it converts it. I think it's 1K, but make sure.
Yeah, 1K should make sense.
Yeah, so make sure you put a heavy enough resistor across it. Like if you put like a 1/4 watt across it, it'll probably burn it up. So get you like a 20 watt resistor or something like that. It'd probably be safe. And that's an easy way. If you have a way to graph it in an oscilloscope, you can do that. Or you can just watch the meter. Well, actually, it's going to happen so fast, you won't be able to see it on a meter. You'll have to graph it in an oscilloscope.
I think we're getting them pretty well covered. Anybody else got questions before we let Chris? He's probably going to go back to work. He's probably not even going to go home yet.
No, I've got a guy just written my dyno right now, so I'll be here until he's done.
Gotcha.
Supervisory tasks. I'll mention this to everybody who's listening here one way or another. If you pull down the either the YouTube or the Facebook, so you can not only listen, but you can see the video, you'll also have a lot of really good information that's added to the chats, which you can see visually. So for example, Justin Brumley had asked about dwell times for IGN-1As at 14 volts, and Brian Barnhill posted the link to the chart that Chris was showing earlier. So there's a lot of really great information that's available via link and other things if you go ahead and pull down and listen to and play back the Facebook version or the YouTube version. The Facebook and YouTube will not be the same because we don't get the same identical questions on both, but that's just maybe a slightly preferred way to do this. And it's always good to see the people who are talking and describing these things, especially when someone like Chris is posting some of the data and doing that share visually. So it makes for a little bit easier to understand content from time to time. Scott Evans, you were answering a question about amperage and all of that. Would you like to go back to this Justin Brumley question about how much amperage and voltage and all that as you were describing on the Facebook thread?
Which question? I've answered so many questions. Which one? Can you be
This
more
was one of the
specific?
most recent ones. It was asking about, amperage, for cruise and idle, and this was actually dwell times. Dwell times.
Yeah.
Sorry.
So dwell time. He was asking, hey, what's a good value to use? On most of our street cars, in general, with IGN-1As, you're trying to keep the heat down while you're just cruising around with it. So I usually start around 3.5 milliseconds with it. And then as I go into wide open throttle, up around 4. And most cars don't need more than about 4 milliseconds to be a reliable spark and not have any issues. As you start to go up in power, you get upwards 30, 35 pounds of boost on an LS. Let's say anywhere between 1,200 and 1,500 horsepower. Maybe it's time to turn it up a little bit sometimes, but often 4 milliseconds will get you clean up into that with no problems at all on a 14-volt alternator, pretty typical 12-volt car. When you start to make a bunch more power and you start to get up around 2,000, 2,500, you start to need a little more, 4.5, 5 milliseconds. Around 5 is where you have to really start upgrading your harness, and you need the thicker wires because that's when you're going to start drawing the current that makes it more than what the factory wire size and what like the Holley harness size and most companies LS1 harness size is going to be. So I haven't really needed to turn it up past 5 in most of the cars I've done. There have been a handful that I have, but for the most part, as long as you've got decent wiring practices going on, you follow the right things for your power, your ground, you try to make sure you're not running noisy things next to clean things, you can get away with considerably small amounts of dwell for what you would think that you would need. Like Chris is saying, they're taking their cars up as much as they can take it because they're high horsepower cars. They're making 10 horsepower per cubic inch on a, 180 cubic inch car, they're making easily 2,000 horsepower out of it. They need every bit of dwell they can get on some of those things at 90 psi. You know, when we're talking 30 or 35 psi, the cylinder pressure is drastically different than when you're at 90. So that's just been my personal experience.
One thing that I think somebody asked, and I think I remember as somebody said, we'll get to that, and we never covered it, was the spark gap question. I know a lot of guys have a question on that, and like, does a bigger spark gap make more power? I get this asked all the time, like, oh, does a bigger spark gap make more power? Like, if I have a better ignition, I can run a bigger gap. Is it going to make more power? I think only in very contained situation, like very few situations, is that really true. I don't, from what I've seen, I don't really see any power gains and the majority of things I've done from running a bigger spark gap. So my go-to gap on anything that's making any kind of power, like whether it's 1,000 horsepower or 2,000 horsepower, I just put them at like 13 and call it a day. Because A, I don't want to have to pull them back out later and re-gap them. And B, like the last thing you want is a car to go down the street, 3 weeks later that you tune and the thing's breaking up because you wanted to get greedy with a spark gap, and the customer's like, why is my car run like shit? So I just put them all at 13 and send them down the road. The only time where I don't do that is if the ignition system is like not great and the idle quality is not great. You might have to open it a little bit, but if you have a good ignition system, man, I don't really see issues with running ultra small gaps on even street cars. I mean, it just doesn't. I just haven't had that experience. I've heard other people claim differently, but that's just what I've seen. So I don't even bother trying to run a 30 gap or a 40 gap or whatever. I just run them at. Now, if it's an NA application, different. I'll run whatever the plug comes out of the box as long as it doesn't misfire. But anything that's forced induction, I just put them at 13 to 16, somewhere in that range. And since I started doing that, I just never have to pull them out to regap them ever. You run them, let them go, and it's done. And like I said, I've never seen. I mean, I've had them at 13 before and opened them up to 22, and not seen any change in power. So to me, there's no reason to even waste your time trying to put a bigger gap in it to begin with. Just start from something that is going to fire every single time and be done with it. That's just my opinion. That's not a rule or a law. It's just.
No, I've run into the same thing, and the logic there dictates why push your luck with a gap, but it also tells you that, okay, so successful combustion to a degree is a yes or no thing, not
Right.
just hey, more spark energy is getting me a little more power in a variable linear behavior. It's not. There comes a point where if you're lighting the mix consistently every cycle, then you don't need any more spark energy. Go find your power.
Like I said, I think
as long as it's not fouling your plugs, you're fine.
I think the only exception to the rule is, like I said, in a maybe a cruising or an idle scenario where you're running a much leaner mixture, and there's not as much mixture. I guess what's the right term? There's not as much mixture density around the plug, so it may be a little bit harder to light. And in those situations, a bigger gap may provide a greater potential to strike across a fuel molecule. Maybe that's why in those situations it runs a little bit better with a bigger gap. But in a boosted application, I've just never seen any reason to try to run a huge gap. I've tried. I've gone so far as like running a car with a 7, a 8, a 9, a 10, 11, with different gaps, projected versus non-projected. And there's a lot of little things there that do make a difference. But when it comes to the gap, like, no, just run it small. If you're forced induction, as long as it idles smooth and it cruises smooth, then just leave it small and run it and have it, enjoy your car. It's way more fun than pulling the plugs out all the time to try to close your gap up when it's hot. So.
You guys happen to see Zach Freeman's question here on Facebook about, does dwell time required go up on a methanol car because of the quantity of fuel?
If it goes up, it's because of the difficulty of lighting the charge, right? Chris can speak to that probably better than me. But that's my simple approach.
Yeah, the more dense it's kind of a there's two ways to look at it, but the general thought process is the more dense the charge is and the more pressure there is in the chamber, the harder it's going to be to light. So yeah, if you may need to get the gap smaller or have more spark energy to cross that same gap because there's more shit in the way from where it's starting and where it needs to end up. It's kind of only way I can think to explain it. I don't know if that makes sense or not, but
Good sense. No, if
makes sense in my head.
if questions are winding down, we'll let Chris get back to work. It's getting almost that time.
Yeah.
Anyone else going once, going twice? All right, stick around. Anybody else? Bill, anybody got any other questions for Chris? No one?
I am completely, confused and amazed, so I'm good.
Well, he's got IGNMAs on his naturally aspirated big block high compression that's presented some different challenges. One of them was cranking RPMs and battery draw when that engine is hot. That sucker takes some serious power, dips a good battery all way down at low voltage when cranking, and that was one of the challenges we've had on Bill's combo is finding an ECU that is happy when that thing sees 7.5 volts during cranking because it's trying to turn over a 580 inch big block Ford that's high compression, and with 12 volts.
We solved
Other than
that.
that,
I have one thing to add about this whole spark plug thing. If you have an ECU that has the ability to fire the outputs individually and be able to test them, use it. If you don't have one, consider looking into the possibility of upgrading to something that does. Highly valuable in setting up your car. When you go to wire everything up, it lets you see that it's all correct. You can test fire your plugs to make sure your coils are working. Just remember, ground the plug to the head somehow, and you can leave it hanging out in open air and actually see it fire spark, and you can find out that, hey, plug 1 is connected to cylinder 1, plug 2 is connected to cylinder 2. Super, super useful in diagnosing weird problems. I had a car that I helped a guy with that he just had 2 plug wires swapped. He didn't know it. He didn't know that he had the inputs going into them flip-flopped, and it was firing weird. It would run, but it would run kind of funky because it just happened to be the cylinder that it was just firing at a time that wasn't detrimental, but it wasn't useful either. And when we found it, it was literally me just going through the test outputs, and we checked each one, and sure enough, found one of them firing, found the 2 that were swapped the 2 wires, worked perfect.
And it's always fun to have your buddy hold the plug while you're doing that test.
Oh yeah,
Kidding, don't do that at home.
Here's another thing that I just thought about that I seen this posted a couple times recently on forums and stuff. Don't crank your engine with no spark plugs in the coils, because not all of them have this problem, but a lot of smart coils will burn up, and the reason is because that charge has to go somewhere, and if it can't go to a ground somewhere on the motor or through a spark plug, it will discharge itself back into the igniter and tear the igniter up. So make sure that if you're gonna crank the engine with the plugs out, at least stick plugs in the wires and have them sitting on something metal, or just unplug the coils, because otherwise you could ruin a perfectly good set of coils.
Don't just use the plug wire, unplugging that to be a way to kill a cylinder if you need to test it. To disconnect the harness going into the coil pack so its igniter is never getting triggered. It'll never draw power.
Yeah, and when you're testing the spark plugs, make sure they're grounded well, because I've seen guys sit there and crank with the spark plug just sitting on the valve cover, and it's not actually grounded to the motor. And it's not going to fire like that, right? You're just burning the coil up. So just a couple of things to keep in mind. I just seen people post some of these situations in the last couple of weeks, and I thought it was kind of important to.
Nice.
know.
All right, we're gonna let Chris go.
All right.
Thanks a lot, Mr. Delgado, for helping us out tonight. Stick around for a few minutes. We've got to chat about something real quick, kind of funny. But
Okay.
I'll go ahead and fade us out. Sorry, everyone, I don't even have music to go out with tonight because I'm remote. We're working on if you follow us, we're tuning the Turbinator 2 car, the gas turbine all-wheel drive streamliner. We did not make Bonneville this last week, but we're hoping to make the October event. So kind of watch my Scott Clark's Facebook, and we'll be kind of covering that. But in the meantime, everybody have a good night. Take care, and we will hopefully see you next week with a really good chassis guest I'm working on. So that's hopefully what's going to happen. We'll make that announcement here in a few days if I can get him on here. But just another chassis episode we're looking to have. So, okay, everyone, take care and have a good night.